Welcome to our 16th lecture. Today we are going to study a new method that's going to be the method of virtual. The nickname of it is going to be the unit load method. This method can be used to analyze various statically determinate structures, including beam, truss, and also frame. And I'm going to focus on the analysis of the truss and the frame by using the method of virtual. That's going to be the problem number 3 and number 4 in our third midterm examination. And again, we start by the work. So what will be the work? Talking about the work, very simple. If you be able to move something from one point to the other point, such as talking about my force, pushing to move it for 1 meter. Okay, the work for that is going to be the force times the distance that I move. That's going to be in the direction of the work. Or the other thing, if you're thinking about this one, have the weight of mg, and then you have the forces move it like this one, lift it up. By this one, what happens? You move your body. Let's call it body. Let's call this one body from the reference point. Okay, you can move anywhere in this direction or in this direction or any this direction. But the work is going to be the weight of this one mg times the distance. So basis upon this one, mg point downward, the direction point upward. So the work on this one is going to be negative work. Anyway, from the reference, again, you move it in any direction, and then you move it forward, you move it for a distance, and then the mg and the direction of movement is in the same direction. The work of this one gonna be positive. Okay, now thinking this one as the reference, thinking this one as the reference, when you move up, the work negative. Okay, but you can, if you release the body, it's going to drop down, right? That means it have the energy stored in it. So it should be able to drop like this one. Let me put this one instead of that one. It can drop like this one. That means at this location, the body get the energy that's gonna be positive. Okay, because it can do the work by itself. And in this location, the energy gonna be in the negative. So work in physics, measuring energy transfer from what? From the reference datum. Okay, that's occur when an object move over a distance by an external force. Reference, very important. Okay, this one has empty. When you lift it up, the work negative. This one possess positive energy. Prove it cannot. Okay, and then when you move this one down, work is positive, energy reduced to negative. Okay, thinking about when you stay over here and you like to climb the mountain. Okay, you climb up the mountain, you're gonna be tired. You use energy. Now, we don't interested much about the object, which is the rigid body. We're going to interested in something that's deformable. Okay, thinking about the beam like this one. Thinking about the beam like this one. For the beam like this one, if there is no forces and moment, it still have the same shape, no change in the shape. However, if you have the moment bend it, okay, bend it, and then following this one, you know that by bending this one, the beam gonna have the curvature. If this is the radius of the curvature, the inverse of the radius of the curvature gonna be d square v by dx squared equal to m over ei. Okay, now for the deformable body, the energy due to the force and moment is in the form of total potential energy stored in the structural system, such as the defect beam. It's stored like this one. Why is it? It's stored energy when you do the work by the moment is bent. It's stored energy because if you release the moment, see, it's going to be returned to its equilibrium position. So, based upon the principle of conservation of energy, the energy due to the moment gonna store in the beam in the form of internal energy. This one you may call it internal potential energy, and internal potential energy is going to be equal to the external potential energy, and I should say this one is due to the moment, okay, and meantime it can be due to the force also, and then they are equal for a conservative system. So, based on principle of conservative energy, the external potential energy equal to the internal potential energy, and should set store in the Russell called structure. Okay, now based on very old concept that you study in physics, we're going to use this in our civil engineering. So let's put it in the scope of our study. Now, talking about the truss, okay, the truss has no forces applied to it. There is no deformation, and then this is going to be in equilibrium. However, when you apply the force and then the structure has linear elastic behavior, just put the force over here. Then the member over here gonna have the tension force. The member over here gonna have the compressive force. Okay, let's call it compression. When the member have tension, this one gonna have elongation, such as this one. You put it have elongation. Then, if you have elongation, there are energy stored in the member. Look it, release it. It's gonna return it back. Okay, and then it will hurt the finger also. And then for this one gonna have the contraction, okay? The elongation, the contraction is going to be a kind of deformation in the truss, right? And then due to the tension force, you can see the tension force and elongation will be used to calculate the energy stored in truss member. And then what going to call it? We do call energy stored in the truss member as the strain energy stored in truss member. We call that UI. And the force, when it's applied to this structure, is moved by this distance. Okay, so you have the force times V. That's going to be the work. Okay, and then if you put it in the negative side, that's going to be external, let's call it energy due to the applied external force causing the deformation of the structure V. Okay, the external force causing the deformation V is going to be in the form of external energy. Actually, it's external work inverse the direction. You got external energy, and it's going to be equal to the energy stored in the Truss member. Following this concept, okay, we will use it later to develop the virtual work. Okay, but before we develop it again, for the linear elastic, you should understand that based upon this one, when the force is zero, no deformation. Okay, and then when you increase the force and the displacement gonna have what? Gonna have deformation. And again, in our study of mechanics of material, we said this is going to be the area under the stress strain diagram. During what? Linear elastic. We call this U sub R. We call this modulus of resilience. Okay, is the ability of the material to absorb the energy. Okay, during the linear elastic behavior, and this one is going to be equal to what? 1/2 of sigma sub proportion strain sub proportion. This is going to be what? The material property, okay, to absorb the energy. Every member of the task gonna absorb energy. The same thing, if you have the beam, previously the beam is in this location, and then you apply the force at the middle, the beam have the move. Okay, then this is the force, this is the deflection. Okay, you can compute the external work and inverse the direction. You will get this term, the external potential energy. Okay, and again, that's going to be external potential energy, and it's going to be negative of the work. Okay, and then this is going to be what? Again, if you do the lab in our material testing, when you test the structure, you have the curve like this one, P and me. For linear elastic, you got the curve like this one. Okay, and then you can plot the curve during linear elastic, and then you get the area over here on the structure, and then this gonna be the work. Okay, that's gonna be, if this is F and this is delta, it's gonna be 1/2 F times delta, and then you revert it, it's gonna be the external potential energy. That is for external potential energy between the force F and the deflection delta. But for this one, you're going to have a bit more complicated to compute it, because this one gonna relate to the energy stored inside the materials. Now, let me move to this one. Let us have a rod, okay, like this one, a rod like this one, and then when you apply the axial force, the rod gonna have this kind of elongation. Okay, when you start over this point, the force is zero. The force is zero. The deformation is zero due to the linear elastic behavior. You will increase the force P. Okay, and then when you reach the force of P such as 10 kilonewton, such as this one, to be 10 kilonewton, you have the deformation over here delta to be such as 10 millimeter. Okay, so an external axial force any F, okay, cause the rod to elongate of the X in the direction of the force. Okay, if you're thinking about it, the small external work due to F is going to be du equal to F times dx. So if the force increase from 0 to P, the external elongation from 0 to delta, P now is 10 kilonewton, delta is going to be 10 millimeter. Okay, and you know that this is a form very similar to a spring. Okay, F equal to Kx. Actually, you know it's going to be delta. Let me put it to be like this one. Delta equal to PL over AE. And then if you said this is going to be P is going to be AE over L delta. P similar to the force, delta similar to the deformation of the spring. So AE over L is going to be the stiffness of this member, such as the spring. Okay, so basis upon that for a typical one, F equal to Kx. Now, this is going to be the integration from 0 to delta Kx dx. And if you do the integration, it's going to be Kx squared over 2 from 0 to delta. So in short, it's going to be 1/2 of K delta squared. Okay, and this one is going to be equal to 1/2 of K delta times delta. And this is going to be F. So it's going to be 1/2 of the force times deformation. Okay, that's going to be the area over here, as I mentioned from the previous one. Now, the concept of virtual work comes from this point. These are typical physics. Okay, Professor Bunari, think if the force just constant, not change, somehow the deformation increase very small, actually very small. It's maybe just 0.1 millimeter, something like that one. So in addition, for a given force P, for this one at 10 kilonewton is a lot, is assumed. I should say imagine, okay, imagine, not assume, the same thing, imagine to elongate an infinitesimal small amount of delta power. Like I said, that's maybe 0.001 millimeter. That's going to be very small compared to 10 millimeter. Okay. Maybe you just have someone to kick out the beam. This one is in cube, right? Someone kick it. Okay, just kick it like this one. The force didn't increase much, but the information occurred. What happened, kid? The extra or additional work due to the force P is going to be this area. Okay, actually, this one supposed to be very small. The picture misleading. It's going to be very small. Okay, and this area is going to be P times delta power. Okay, this is going to be the light blue area. And then this concept again, okay, maybe reverse. Okay, this one taking the constant P with very small deformation. Okay, and then next time they said for a given deformation, okay, increase the force very small, and that's going to be the concept of virtual work later. Now, for the moment, okay, this one for the task member, for the beam and the frame, the deformation of the beam and frame is due to the bending moment. So thinking about a member have a spring over here, and then you apply the moment M, then the angle gonna increase. When the N increase, the angle can be also increased. Okay, so for a very small moment M over here and have the theta over here, the area under the curve is going to be external work. Now, you may say again, M can be the stiffness due to the rotation time any angle theta. Again, following this one, M equal to Ks, K of the spring over here, time d theta. So this one it will be integration from 0 to theta, K sub S theta, d theta. Then you get this one to be equal to Ks theta square over 2 from theta to theta. Then you have this term, and this term is going to be 1/2 K sub S theta times theta. This is going to be 1/2 times M theta. That's going to be the area. Okay, when this one is M, this one is theta under the glass. That's going to be external work. Okay, now you have this one, the area. And then the same concept. If the moment still constant and there is the infinitesimal amount of rotation theta prime occur over here, then the area of the curve will be in this yellow, and this can be computed based upon this equation. Just M times the difference from here to here to be theta prime, and theta prime is going to be very small. Again, the picture just misleading. Actually, the yellow is going to be very small. Okay, the system, both sides still be in equilibrium. Okay, you can compute the extra work from the moment from this equation. Now, thinking about this one again, okay, this one again, and then you have the linear elastic behavior. This one may be the Truss member and maybe the rod, okay, or bar or column that's subject to axially loaded. Okay, this always called axially loaded member, or you may call it two force member. It's going to be the same thing. Okay, and it's made by homogeneous material. Truss most of the time made by aluminum or steel. You never see the truss is in the form of reinforced concrete because it's hard to build it. Now, you have the Hooke's law, and if you cut it over here, okay, if the force over here, external force is N, you will have summation of F sub y equal to 0. The internal force over here gonna be N. So the stress is gonna be N divided by the cross-sectional area A. And then that is gonna be time modulus of elasticity. And then we have over here delta divided by the length L. That's gonna be the stress. Okay, so you have this equation. Now, you may thinking about delta equal to NL over AE, as Ajahn just mentioned. Okay, or you may thinking N equal to AE over L delta, and this one gonna be the stiffness. Okay, of the Truss member. Now, going back to what we discussed, the external potential energy is going to be the area under the graph when this one is and this one is delta. This is the external potential energy. And external potential energy is equal to what? Is equal to this one. Let me take this one. U sub I. This is going to be equal to the state energy stored in the Truss member. Okay. And then following this one, you just take the delta and put it over here for a given Truss member, for a given Truss member, for a Truss member. You have this to be the energy stored in the Truss member when the Truss member have the internal force F and has the elongation delta. And then the Truss usually has many members. Okay, has many members. And the member of the Truss can be classified this one member, this two member, this three member, four member, six member, seven member, eight member, nine member for a task subjected to a force, and then that's gonna cause compression for the top member, tension on the bottom member, and also kind of deformation in the member. Then usually the total energy of this one is going to be U sub I equal to summation of the number of member and then N sub I square L sub I over to A sub I and E sub I. Okay, again, Truss can be separated into member. So when you calculate for the total energy in the Truss, you got to use summation. Okay, this one just for a Truss member. Okay, now for the beam different from the Truss because the beam has continuous. Okay, from the left to the right, and we call this X meter. Under the application of the force, this beam will have this kind of elastic deformation, and then we should say elastic deformation, or you should say elastic curve of this one is a continuous function. Okay, you can write the equation represent the elastic curve of this one. If you say this is V, this is X, the V is the function of the X. Okay, different from the task. The task you can count member 1, member 2, member 3, member 4, plus the beam will be that. And then when you bend it, the beam gonna have this kind of deformation. The top gonna be in compression, the bottom gonna be in tension. Okay, now we have the elastic beam theory. This is for the beam for the linear elastic behavior, and also made by the steel or aluminum, which is an example of isotopic homogeneous material. Again, come to this equation. Okay, we're going to be what? We're going to determine the external potential energy. From our previous discussion, external potential energy is going to be the area under this graph, when this is M, this is theta. Now, you may put this one, okay, and then you may think for a small element, for a differential element, okay. One, this one equal to this one will be in the form of differential energy, okay, for a differential element. The energy stored in the differential element gonna be the differential state energy. Now you just put the theta, very small deformation over here and rearrange it. Then you have this form. And then the total energy, the total state energy stored in the beam, stored in the frame member due to the bending will be this one. Now, this one have integration, okay, because integration represents the continuous function. Since the deflection is the continuous function, beam and frame require to have integration to compute for the energy stored in the beam, the frame. I like the task. Okay, we just use summation because you separate the task into task member that can calculate. Now, we move to this one. Okay, before the occurrence of the principle, for the method of virtual work, okay, there is the principle of work and energy again. For the beam, this one handle beam with linear elastic behavior, just put it, point the load over here. You have this kind of elastic curve. So this one is fixed, no deformation. Theta sub b equal to vertical v in y direction or x direction also equal to 0. And then the beam have this kind of elastic curve. And then at the end of this one, the free end, okay, the free end, the beam subjected to the force P. Then following this one, if you plot a graph of P and deflection, okay, again 0 when you increase the force for linear elastic, and then you list the force P over here, you list delta A over here, the area under the graph is going to be 1/2 P delta A. That's going to be external work, okay. Also, it can be classified of external potential energy, okay, if you inverse its sign. Now we just compute for the state energy. From the previous slide, we have this one, okay. The energy stored in this one. Why you notice? If you release the force, it's going to be turned back. Okay. Now we need to cut this one as the position over here. Okay. Let's call it x. Summation of the moment equal to 0. Take this one positive. M is going to be minus px. Then you just cut M over here, okay, and then take a square. You get what? You get this equation, and then if you like it, it's gonna be T squared over 2 EI integration of x squared by dx, and then if this one you get it, how come I like it over here, and then you take this one, it's gonna be T squared over 2 EI x cubed over 3 from what? 0 to L, and then you get what? You get T squared over 6 EI, and then L cube. Okay, you got this equation P squared L cube over 6EI. Okay, now when you get the result like this one, okay, P squared L cube over 6EI, they must be equal. Just put them together, okay, and then you get the result of this one to be PL cubed over 3EI. And then go back to this one. This is going to be the same result from the deflection table. Okay. Oh, Ajahn, this is very powerful. No, this one is a special case or no note of this one. If we have more forces, such as we have anosity, okay, applied at the length of L over 2. Now, this one, okay, will require another 1/2 P delta over here to be C, okay? And then you can do the integration. Since this one has 2 unknowns, okay, so you cannot solve the equation of the principle of conservation of energy directly because there are 2 unknown to compute. So the development must be done. Okay, let me stop my first part over here. Principle of virtual. Okay, let me take a break over here. Now, we come to our subject. The principle of virtual is going to develop to be the method of virtual. We come to the work of Professor Bernoulli. If you recall, you study his work in fluids mechanics and hydraulic. Okay, he is one of great engineer at this time. And he bases on what we discussed about the principle of conservation of energy. And he developed a very important concept. First, thinking about the elastic beam. And this elastic beam subjected to many forces, okay, maybe P1, P2, P3, P4, P5. Under the application of the force, the beam has elastic deformation. Now, the beam has this kind of elastic deformation. And based on elastic deformation, there are deflections, delta 1, delta 2, delta 3 occur on the loading point. Okay, and he said he preferred to determine the deflection at point C. Okay, at point C, you also have the deflection delta C also. This one is in equilibrium. Okay, and then for a small element that is inside the beam. Okay, let's take a small element over here. Okay, since this one is on the top portion of the beam, okay, the force applied to it is going to be the compressive force. Okay, that's going to be distance y. That's going to be in compression. Okay, he imagined for this beam during the deformation, if there is a 1 unit force applied to this beam during this kind of deformation, thinking about again, okay, if the force is here, deflection is here, linear elastic occur over here, okay, for a constant force, and there is an assumed deflection. We have this area, okay, this extra work is going to be P times delta pi. Now, he assumed in opposite direction. He assumed the force applied into it with the same delta sub c. Okay, by the same concept, he said this is going to be what's so-called external virtual work. We said that's called external virtual work. He used the word virtual over here because this one he imagined it. Okay, just imagine it. Okay, and then the unit force also has the same element, over there with the internal force of U. Now, there is the internal force of U occur due to one unit. And he said, due to the actual deformation over here and time the internal forces due to the imagine, okay, this one you time it, you will get the internal virtual work. Again, he used the virtual because this is the imagine internal force. Okay, now he get what? He get the first term over here to be 1.0 times delta sub C over here. Okay, and over here is going to be equal to the internal force due to the internal moment times what? Times the real displacement dl. Okay, now what's going to be this one? What's going to be this one? Depend on type of structure. Okay, the equation for this term will be changed based on type of structure. For the task, the U is going to change to the small axial force. And then for the task, you have delta equal to NL over AE. So for the task, DL is going to be NL over AE. And since the task must count the number of members, so for the task, you got to be N equal to form 1 to the number of this one. Let's put it into X. So this is N-I, capital N-I, L-I, E-I, A-I, for example. Okay. But for the beam, this one must change. Okay, we will discuss later. Okay, what is going to be the U? The U for the beam is going to be the bending moment M sub I. Okay, since the energy stored, the deformation of the beam not in the form of dl, it is in the form of d theta. Okay, by dx. And this is going to be M over EI. So this is going to be capital M dx over EI. And for the beam, the function of the deflection is a continuous function. So this one integrates from x equal to 0 equal up until x equal to L. So this term for the beam and the frame gonna be the integration from 0 to L. This due to 1.0 unit load. And this is due to the real applied force and time dx over EI and integrates force over T. Now you have two important equations. And the equation for the method of virtual work. Why is called the virtual work? Because for the structure that is in equilibrium and imaging of 1.0 unit load put into that structure. and due to the linear elastic behavior, okay, these two can be combined and should mention about the principle of superposition. อาจารย์ I won't believe it. You can prove the result, okay, of this method with the double integration. Okay, if the result is correct, the method gonna be correct. Now, believe it or not, in short, to find the deflection delta sub C of the beam, okay, we imagine virtual unit load applied at the point that you prefer to determine the deflection. Okay, then for the linear elastic behavior, okay, that is in equilibrium, external work due to the virtual unit load. I call this one again external work due to virtual unit load to be external virtual work. Okay, that's gonna be equal to the internal energy due to that virtual unit load. That's called this one. We call it internal virtual work. Okay, and for this one, we just take this one with this deformation, and this is the portion of the external work. And then there are the internal, okay, virtual work due to the unit load applied over here. We have this unit load U and have this kind of real deformation. So this is real time virtual. We call it the internal virtual work for this portion. Okay, and you can see the term on the left hand side, the red, you don't do any calculation. Okay, for this one, your work is going to determine two things. One, you need to determine the internal force or internal moment due to 1.0 unit load. Okay, due to 1.0 unit load. And you require to what? You require to determine the real deformation. That's again depend on is the Truss, okay, or yes, USS Truss or beam and frame. Again, for the Truss, DL gonna be NL over AE, okay. But for the beam and the frame, you got to change this one because this one change to moment. This one got to change to d theta, and again d theta is gonna be M over EI dx. Then the term over here is gonna be the real deformation. You got to determine what the normal force due to the real force, the moment due to the real forces. And then for following this one, there are something I should mention again. Let me illustrate all of this. There are two things, okay, on this virtual work equation. Okay, the 1.0 and U. 1.0 is the virtual unit. Okay, this is going to be the virtual unit load. The virtual unit load costs what? The virtual unit load costs the virtual internal force and also moment. It can be U, it can be M. And then there are the actual or real deflection. Okay, this is what we are looking for. Okay, and for this one, you should be able to determine the actual or real deformation DL. So the procedure of the calculation will be first consider the structure. Okay, it can be, let's assume first to be the task. Okay, we have the task, and our task may be this one, and then our task subjected to a force of this one, or force of this one, and for sure, but the force of 30 kilonewton, the task must have the elastic deformation, as Ajahn draw this one show you guys already. Okay, the deformation occur over here. This one for the elastic curve. Okay, you like to determine what? For example, if you prefer to determine the deflection over here, let's call V sub C. Okay, then you got to separate this task into two tasks. One is going to be the task that's subjected to the 30 kilonewton. Now, over here is thin and roller subjected to this force of 30 kilonewton. And then you must task another task, the same one. Okay, the same one. By principle of superposition. By principle of superposition, you apply what? 1.0 unit load over here. You apply the force of 1.0 unit over here. Then let me change this one to be delta sub C. Then what you have over here is what? The 1.0 times delta sub C is going to be 1.0 times delta sub C. Okay, that's going to be external virtual work. Okay, so the second step I would like to use after you consider the structure and write the virtual work equation, right? The virtual work equation 1.0 times this one gonna equal to what? Equal to the summation. Okay, again the summation I talking from I equal to 1 to x of what? Of the force that occur over here. I call this one n sub I. Okay, so that's going to be force n sub I. And then for what? Times the force of this one for the real structure gonna be n sub I. And then L sub I over A sub I, E sub I. So the second step, okay, determine n sub I. And what's going to be the third step? Determine small m sub I. Determine, okay, small n sub I. And then the last one that you put or result, okay, you compute, okay, compute for delta sub C. The step gonna be something like this one. Okay. Now, following this one, let me take you to the first. Let's put it in the example over here first. It's better. Okay. Now, following this one, let's take a bit more for the beam and the frame. Okay. Things gonna be kind of same. We're going to apply 1 unit of force. If you prefer to determine the deflection delta or V. But if you prefer to determine the slope, virtual unit load gonna be virtual unit moment. Okay, this is gonna be force of unit 1.0 unit to determine the deflection. But if you like to determine the slope, you got to put the virtual moment. Let me put it to be virtual force, and this one for virtual moment, virtual moment for this one. Now, if you determine the slope over here, this term will change to small m. This term will change to d theta. Okay. Now you compute the d theta to determine the slope. Okay. That's gonna be the equation for the beam and for the frame. Now, let us move to the task first. The task is going to be easier, okay? And then for the task, when it's subjected to the force, the task will have the deformation. And the deformation occur at the joint. And for the task, you have only vertical and horizontal displacement. Okay, and also we have this type of example testing for the deformation of the task. This one, when the load is 0, and when you increase the load, the deflection larger and larger, and up until the failure. And also, you can use the computer to simulate, determine the deformation of the task. Okay, and also you can determine the axial force in the, this one is wrong, in the task also. Okay, the red is in tension, this one in tension, the blue is in compression. That's gonna follow, we have static. Okay, so deformation can compute from the computer. Deformation can measure in the laboratory. You have that experience in the material testing laboratory, and deformation can compute manually. Now, for the task again, okay, we have what? We have to consider the elastic curve of the task. This one actually is supposed to be something like this type of deformation, and then the task subjected to the force P and cause the delta at point A. Okay, now using the principle of superposition, imagine a unit force applied over here. Then the unit force over here times the delta sub A, times the term delta sub A. This called external virtual work. Okay, this called again external virtual work. You're looking for what? You're looking for delta sub A. The term on the right hand side is the term you are looking for. But the term on the right hand side, what's going to be what? For the unit load, there is the tension force, compressive force occur here. And this is going to be N sub I. So this one change to N sub I. Okay. And then there are deformation. Okay. In task member on the top, that's gonna be contraction. On the bottom, gonna be elongation. Okay, that's gonna be the term DL. And then you have sigma equal to E epsilon. Okay, sigma equal to N over A equal to E dl over L. So dl delta L or dl is going to be NL over AE. This term change to NILI over AIEI. So for this one, you got to determine n sub I, capital N sub I. For this one, you got to determine small n sub I. So basis on of that, you got this equation. Okay, and now we move a bit to a more complex one. Let me say this is virtual unit load. You got to put it at the point you are looking for the deformation in the direction, okay, at point A, and in the direction of the required deflection, okay, and then this is going to be your forces in Truss member due to the 1.0 unit load. This is going to be this one. And then for the real structure, you can determine N. So for this one, you can determine from over here. Then you just put everything together, you can determine delta sub A. Now, let me put it in the first step. Anyway, you start by consider the task. Consider the task, and if possible, draft draft the elastic curve, okay, to provide you the insight how the structure gonna deform, okay, like I put it over here, you will get this type of deformation. And then analyze the task to determine this n. And then analyze the task to determine this small n. Okay, and then just put them together in the, this is the virtual work equation. Okay, and then in short, coming over here, we're going to determine the vertical displacement at point B. Okay, you have the task, right? So this is V sub dx equal to V sub dy equal to 0. V sub ax equal to V sub ay equal to 0. No movement. And then following this concept, you can see this one and this one gonna be zero force member. When there is the zero force member, there is no deformation. Now, you may see the task put by the force like this one. For sure, this one gonna have the vertical displacement at point B, okay, due to the force. And also, it should have this also deformation. This is going to be the horizontal displacement at point B. Okay, if you assume, why you assume that? I assume this one because under the force, this one gonna be in compression. This one gonna be in tension. So this one should have this kind of deformation. That is that. Okay, let me move it. Okay, this one gonna have this type of deformation, and I think the other member, this one should have shortened. Okay, the yellow may have elongation, the purple gonna have contraction. Okay, and then I can assume the deformation in the form like this one. This is gonna be V sub C H for the horizontal, and this is gonna be our our V sub C Y, or you may see this is going to be V sub C V, vertical and Y, the same thing. And then the truss is the steel, okay, and the cross-sectional area of the member specified over here. Now, write down what's so-called the virtual work equation. Just put it, the virtual work equation 1.0 is going to be the force that's going to be over here. Put the 1.0 to the point. Okay. Sorry, this is point B, not point C. Point B, not point C. Sorry, point B, point B, point B. This is point C, point C, point B. The deflection of point B is gonna be here. This is V sub B or delta sub B, and then horizontal gonna be here. V sub B H. You put the 1.0 force at point B in the vertical direction. Now, 1.0 times delta sub B is going to be external virtual work. And then for a given pictures over here, you may determine N sub I. This is going to be N sub I. For the one over here, you can be small n sub I over here. Okay. And then where is L? Just take L sub I. This one is 1.2. This one is 1.2. Okay. This one is 0.9. 0.9 and 1.2. This is going to be 1.5. Okay. A sub I. Over here, and E is over here. The problem is there are a number of calculations of this one. It's better to put it in a table. Okay, so do the computation, capital N over here, small n from here, and then put into the equation. Now, you do the calculation for the capital N. Okay, you may use any method such as method of joint to compute it. Just take this one at point C. Applied force gonna be 22.5 kilonewton. And then, as I said, CD supposed to have in tension. So this is gonna be N sub CD. And then this member should have in compression. So you have this one to be N sub AC. And this is what this is gonna be the distance of 1.2. And this one is 0.9. So this is 3, 4, and 5. Okay. By using the method of joint, which equation you're going to use? This is x, this is y. You guys know very well. You should start with summation of x sub y. Okay, equal to 0. You take this one up, this one n sub AC times 3 over 5. So upward is positive. N sub AC times 3 over 5 upward. And this one going to be equal to 22.5 equal to 22.5. So your N sub AC for this one going to be 22.5 times 5 over 3. You get this one to be 30 kilo. Oops, sorry, 37. 37. That's this one. 37.5. Just check it. Okay. Put it into your calculator. Do you get the result of 37.5? and this one gonna be in compression. And when it's in compression, put it into negative. Important. Okay. Put it into the negative. Now, the second one, summation of x sub x equal to 0. You're looking for n sub cd. Now, n sub cd. This one gonna be in the opposite direction. This one n sub ac and then times 4 over 5. Okay, and then you have this one equal to 37.5 times 4 over 5. You get this one to be 30 kilonewton, and this one gonna be positive. Okay, positive. Now, you get the result, and you can check, okay, for the member AC over here, okay, you can divide the force by the area. The area, you get the stress 60 megapascal. That's less than yielding stress, so it's linear, elastic. The same for the CD on the top, okay, you divide 30 kilonewton by the area. The stress gonna be smaller, and that's gonna be linear elastic. Okay, now for the 1.0 unit load, okay, you can see following this one, this is gonna be zero force member. Okay, and then the force over here, will be going to be what? This is downward 1.0. The force over here is gonna be small n CB. This is gonna be 1.0 and in tension. Okay, this member is gonna be in tension. Okay, due to this force, it's gonna be this one, and then this is gonna be the force. Then you can transfer the force and apply it over here to be 1.0. Now, the same load applied at the same point, but the magnitude reduced by 22.5. The result over here gonna be 30 divided by 22.5 positive. This is gonna be minus 37.5 divided by 22.5. You will get the result to be this one. And then you get the result to be this one. Okay, you don't need to do the calculation again because the 1.0 applied at point C, the magnitude reduced by 22.5. So the n small n sub I will be capital N sub I divided by 22.5. Then you get the result. You put them in the table. Okay, if not, you got to write very large, long equation. By putting the table, you put it the member. Okay, the first one you put it to be this one for the AC. Okay, this is AC. This is AC. Okay, this AC. The AC is what? The AC has the length of what? This is 1.2. This is 0.5. No, 0.9. This is gonna be 1.5 meter. Okay, the area is gonna be this one. Now, for the member DC is over here. Okay, DC is over here. Is 1.2 meter. Okay, you prefer put it into the millimeter, something 1,200 millimeter. The area, this is 1250. This is between 1250 square millimeter. Now move to the AB. Okay, AB is over here. Okay, AB have the length equal to 1,200. The area of this one 1250, and the last one that we have is going to be BC. Okay, BC is over here. The length is going to be 900 millimeter. Area going to be 625. Okay. Now take the n sub I. Okay. Take the small n sub I into the table. Do the calculation. Do the calculation. Okay, for this one, is going to be this one times this one times L. Okay, times L divided by 625 for sure. This is going to be the AC. You get the result of this one for the AC, and result we also want for the DC. Okay, you just combine them together, and then you get this one to be 0.94 millimeter. That's it. Okay, to compute the deflection of the truss. Okay, very simple. Okay, you get the result. And if Advanced get this one, you will get the elastic curve like this one. Just specify this one, 0.94. Okay, and you should be able to determine V sub V in the horizontal direction. How do you do so? Okay, 1.0 times delta sub V in horizontal direction. Okay, it's going to be equal to summation of small n sub I, and then the same term. No need to do any calculation for n sub I, L sub I over A sub I and E sub I. Okay, this one to be what? N sub I can be computed over here. Use the same result. Okay, but for the small n sub I, you got to take this one. Just take this one out. Okay, just take this one out. And now you apply the force of 1.0 unit load over here. 1.0 unit load over here. Okay. And then if you apply force 1.0 unit load in this horizontal direction, this is gonna be 0. Okay. And then if you cut the joint B, you cut the joint B over here. This is gonna be 1.0. And this is going to be the force small n in the member A, B. Okay, and summation of f sub x equal to 0. This is going to be 1.0 positive intention. And for sure, there is no force in this direction. N sub this one, B, C equal to 0 if you do the summation of f sub y equal to 0. And since there is no force over here, this is 0. This is 0. Okay. So let me take you back over there. We have only force in this one to be 1.0. Okay. Now let me take you back over here. We have another one, n sub I in the horizontal direction. Okay. We have only for the AB 1.0. This is 0, 0, and 0. And you can see n times this one 0. N times this one is 0. 1.0 times this one is 0. 0 times this one is 0. So delta sub BH gonna be 0 plus 0 plus 0 plus 0 is gonna be 0 millimeter. Okay, now I get the result for the displacement at point B in H horizontal direction. I go back over here. Okay, and then go back over here and let me erase off. This is going to be 0. This will be 0. Wow. Okay. And now you can draw the elastic curve. Okay. Going to be similar to this one, but the over here, gonna be here. Just put it over here. And then over here, gonna be in this one. And then that is going to be our new correct elastic curve. Okay. And then how come you draw the first one incorrectly? I don't know. That's dark. Okay. This is going to be a correct. Okay. If you increase the load for 2 times, the deflection is going to get double. Okay. And then the stress will be in the linear elastic. Okay. Let me stop first. Okay. Show you. Okay. Okay. The third session. We come to another example. The previous one is the cantilever truss. This is a kind of simple truss, and we use a number of cantilever truss and simple truss in our real life. Coming to this one, we determine the vertical and horizontal displacement at joint B, okay, of this steel truss. The problem have the A. All of the member have the same cross section, different from the previous one. Okay, this is supposed to be easier. And then the steel have the modulus of elasticity of 200 gigapascal. Then, due to the force 30 kilonewton, the bottom portion gonna be in tension and the top portion gonna be in compression. Then tension produce what? Produce elongation. So I believe we gonna put downward over here and have a horizontal displacement like this one. Okay, and this one also, but the vertical displacement should be less than, okay, this may be delta sub V V, okay, this one may be delta sub V H, then you have delta sub C vertical, this one for sure, less than delta sub V V, okay. And then you should have what? Another additional elongation. And this is gonna delta sub CH. And I believe delta sub CH larger than delta sub BH. Okay, because elongation plus elongation. And then additional elongation occur over here. But for this one, delta sub dv gonna be 0. Delta sub dh gonna be larger than delta sub ch because every member have tension. Okay, in my opinion. Then we sketch the deformation. Put the ruler and sketch a straight line link between the joint. And then you should get this for the draft of the bottom chord. And then for the top chord, okay, it's supposed to be the same downward and horizontal. Just take this one. The one over here supposed to be shortened due to compression. Okay. And over here also should have this kind of deformation and link them together. You will get all of this kind of elastic curve for the truss. Okay. Then Following this elastic curve, we are looking for what? We are looking for this one. Vertical, horizontal displacement at point B. Okay, you write down, to get this one, you write down the equation for delta sub BH 1.0. Delta sub B vertical is going to be summation of small n sub I. And I should say, this small n sub I can be computed, okay, from a unit load at point B, okay, in the vertical direction, and then times what? Times capital N sub I. This provides you the capital N sub I, and then L sub I. L sub I also determined from here, and then A sub I and E sub I. We know it. They are constant. Now they are constant. Okay. All members have the same AE. Now you do the computation for this one reaction, okay, and then you use the computer. You can get this one plus 20, this one plus 10, this one plus 10. Ajahn, in the examination room, you can let me compute. Don't worry, only capital N sub I or small n sub I. Only one of them, not all of these two. Okay. And then you got to put it. If tension, put it in positive. If it's in compression, put it in negative. Okay. Beware about that because the signs are important in the table. Now, you have this one. Compute for small n sub I. Put the unit load, okay, at point B in the vertical direction. Oh, Ajahn, this 1 kilonewton is in the same as this one. Yes. Now, n sub I is going to be capital N sub I divided by 30. Okay. Now, you have the result for this one. Just divide everything by the 30. 20 divided by 30, 2/3. 10 divided by 30, 1/3. Okay, and the same thing. Small n gonna be capital N divided by 30. And then the result gonna be something like this one. But you got to be very careful when you put it in the table. Okay, very careful. For the AB is over here. Okay, just take this one AB, and the length of AB gonna be 3 meters. So take 3 meters. For the BC, okay, take the second one. For the BC is over here. You take this one for the BC. Again, 3 meters. Okay, for the CD, you have this one, 3 meters. And for the DE, just take this one for the DE. Okay, DE is here. This is 3 meters. So this is going to be square root 3 meters times 3 meters. It's going to be square root of 18. Okay, you got this one, 4.243. And do everything the same thing. Okay, for the EF, you just take it over here, EF. Okay, and then what? This one for EF, 3 meters. Do everything like this one. Then very careful on this one. Okay, very careful on this one. For the EF, we have minus 20. Okay. For the DE, okay, you have over here minus 14.142. Okay. For the AB, this is for the AB positive. Okay. Okay, later it must be multiplied. So negative, positive gonna be important. Then for the n, do the same thing. Do the computation. Negative times negative gonna be positive, something like that one. If you put wrong side, the result gonna be wrong. Then sum them together. อาจารย์ how about AE? Don't worry. Don't worry. Okay. Since AE, they are constant. You may put it to be the divider later. So you get the result of this one to be this TO 9.69. Oh, I got positive. That means this one is downward. Okay. Following what? This following the direction of the unit load. The direction of the unit load gonna forward the direction of the results. Okay, then you have this one, and then put the AE. This is 5.2 millimeter. Okay, now downward. Okay, follow the direction of the 1.0 unit load. And then you have this kind of deformation. You have the result of what? Your result is over here. This is going to be delta B vertical. Then there are deflection over here. Delta B horizontal. Okay, can you determine it? Very easy. Just put 1.0 unit load over there. Okay. Anyway, the AE. Okay. The good thing about setting the AE equal is going to be what? For ease of construction. Why? Why is for ease of construction? Because all the member gonna be the same size. But the bad thing is what? The bad thing, the structure is like more expensive because some member not require that's too big. Okay, that is a bad thing. Okay, good thing, more expensive. And then if you get this equation, Ajahn may say, if we limit the vertical deflection to be only 4 millimeter, previously we get 5.2. This is seen too much. You like to reduce it to be 4.0. So what happened? The area gonna get bigger, right? So just take this one to be 4 millimeter. Compute for A. A gonna be bigger. Okay, now every member must have at least 384.1 square millimeter. That's bigger than the previous one that specified only 300. Okay, now can we use this exact number? No, go to the steel table. Check it out. What you get? You should get this one. This is 3.25 square centimeter, or this is 325 square millimeter. This too small. Okay, and this one 414 square millimeter. This is okay. Okay, a bit larger. Can we use 5 to 3? Yes, you can use, but that is too big. Okay, too big is mean too expensive. Now, let me take you more. Okay, for the horizontal delta B sub H. The capital N sub I gonna be the same. This one gonna compute for the 30 kilonewton the same. But for the small n, take the 1.0 unit load, apply at point B in the horizontal direction. Okay. And following this one, you can see, okay, when you apply the force like this one, you have only A sub X equal to 1.0. Okay, the force A sub Y equal to 0 d sub y equal to 0. Okay, and then following this one, you have point A, and then A sub x equal to 1.0. You get the force over here. N sub AB, summation of x equal to 0. This is going to be 1.0 positive. Okay. For the force over here, AF. Okay. So for this one, N sub AF, this is going to be this one, 45 degree, 1 square root 2. Since this is 0, okay, you can see the component of this one, n small n sub AF, and times 1 over square root 2. Summation of sub y equal to 0. N sub AF gonna be 0. This is 0. This is plus 1. Since this is 0, this is 0. This is 0. Okay. Since this is 0, this is 0. This is 0. This is 0. This is 0. And everything 0 except this one is 1.0. You have what? N sub A B equal to 1.0. Go to the same table. Okay. You have only 1.0 on this member. Put it in the same table. You have the term over this portion have the horizontal deformation. Then you get the result to be 60 over AE. Now, you get 1.0 millimeter. And this is what? This is going to be the one will move in this direction, the same direction of the 1.0 unit load. Okay, the same direction because it's positive. Okay, now your result gonna be something like this one. This is going to be 1.0 millimeter, and the vertical is gonna be 5.2 millimeter. The absolute is gonna be square root 1 square plus 5.2 square. That's going to be 5.3. And the resultant deformation is going to be in this direction. Okay. Now, if I can prefer to determine this deformation, delta C sub H. Do the same thing. Okay. Just take this one delta C sub H. Put 1.0 over here. And this is going to be the unit load. Okay. Capital N sub I going to be the same. And then following this calculation, you will get this one to be 1.0, to be 1.0, to be 0. And everything going to get 0. Okay. The computation going to be 60. The same as before. Plus additional member BC. That means delta sub CH gonna be larger than delta sub BH. It's gonna get 90. Okay, you get this one for 90. And for sure, if you determine delta sub BH, it's gonna be get bigger than delta sub CH. Okay. Now, I have 6 more minutes. Let me move to the temperature. Okay. You may go out over there. Okay. We have the loop, and our loop is transparent loop. And then there is the smile sun. Okay. During the summer, put the sunshine onto the loop. And then the member over here gonna be what? Hotter than, for sure. The member on the bottom. Okay, the purple gonna be hotter. When the temperature change, okay, the Truss member also have the change in the length. Increasing in temperature get longer, colder get shorter by that concept. in Poland, okay, during the summer. We are about here, okay. The temperature should be larger than the typical one. Now, if the top portion get the heat, what happens? For the change in temperature, the change in the length is going to be alpha L delta T. Okay, if the change is positive, you should get the elongation. Okay, alpha is what? Coefficient of expansion of the matrix. Okay, delta T is over here. L is going to be the length. So basis upon this one and virtual work equation. Okay, you just take this one over here. You can compute for the change in temperature. Okay, it's important. Okay, especially for very high temperature. Now, let's take the example. Okay, compute the deflection of a given point on this task due to the change in temperature. Require you to put 1.0 force into that point, such as point C, in the given direction, like this one, 1.0, and then alpha open in the table. This one given L from the class. Okay, still has 12 10 minus 6 per degree Celsius. Now, from this equation, okay, you got to what? You got to compute for N. No, there is no external force. Okay, this time there is no N. No N, let me show. But you got to compute for small n. We got to determine vertical displacement at joint B. So over here, you got to put 1.0 unit load at that point. Then the same computation. This is what n sub I equal to the previous one divided by 30. You get the result. Okay. And then only this member has the change in temperature. The author won't have temperature change. You don't need to consider the author. Okay. You now only consider for the member that heat up. Only this member. So take this one negative. Okay. This is small n. This is going to be the alpha. Okay, this is going to be your delta T, and this is 3 meter. The change going to be negative. That means what? If the loop, top loop is hot, the deflection in the upward direction. So heated loop is good. But colded loop is bad. Okay. That means I show you the picture of the collapse of the civic center in America due to the snow on the top of it. Okay. First, maybe due to the weight of the snow. Second, maybe due to the contraction of the top member, causing the downward deformation of the truss. Okay. And this is going to be a good effect for Thai, Myanmar, Philippines in our tropical zone. Okay. Okay. If the temperature increase for AF, okay, all the top member get hot. Don't worry. Okay. You just sum them together and then you get the result. That's going to be a good effect. Better than. Okay. Now, the last one for the fabrication error. Okay. Sometimes the member is too long and it's only occur on the belted joint and riveted joint. That means what? Nearly never happen in Thailand because we use the welding. Okay. We use the welding. If it's too long, they just cut it to a given length and weld it. But for the bolted joint and riveted joint is required to force it into the position. Okay. If you put it, if it is the delta L fabrication error, just put it over here. Very simple. Okay. From the previous one, do the same thing. Okay. Compute, put 1.0 to the point in a given direction and then compute for the small n. Now you have the same one. If VE is too long, okay, it's too long. Okay, this is positive. You got to what? Compute of what? Deflection at point B over here, point 1, point O unit load. Get the same n. And only this member have the problem is have the force of 0.475 positive. So put it together, you get the result to be 4.7. This is going to be downward. So long member is not good, increasing the deflection. Now, you can combine the first problem, the second problem, this is only this member, and the third problem together and get the result. Okay. Don't worry, I won't put the temperature and fabrication error in the examination. Just teach you for your knowledge. Okay, later you may explain about what loop is good. Reduce the deflection. Okay. Longer member is bad. Okay, increase the deflection. Okay, but in Thailand, we mostly use the welding, so we don't have the problem with the fabrication. We have only full effect of the hot loop. Okay, okay, that's all for today. Any questions? Next time I will come showing you how to solve the problem, but it's going to be very quick. Okay, and go to the beam. And next week I got to finish the plate, and then the week of 11. Let's say it's going to be Sunday night. Okay, we should have the third examination. Oh, Saturday night, if you can, I will give the exact date later. Okay, thank you.
We are going to work on the analysis of the Truss. In these clips, Ajahn will use the method of virtual work, which may call it the unit load method. That's going to determine the vertical displacement at joint C and joint D of this truss. And it said each member have constant axial stiffness. So this time all the EA are going to be constant and the calculation going to be a little bit easier. And then they asked us to draw the elastic curve of the truss properly. Anyway, before we start each problem, we should imagine which way the truss is going to deform. Okay, this time the A is going to be the pin and the E is going to be the pin. When the truss subjected to the force, you may see the top chord going to move like this. When the top chords move like this, that means the bottom chord going to get shortened. So for sure, we can make assumption that a top chord going to be in tension and this bottom chord going to be in compression. Okay, and preliminarily we can assume the deformation of this point D will move downward here and may have some horizontal displacement, but it's going to be small compared to the vertical. So this portion of the truss will have to deform like this, and then the B should be here, the D supposed to be here, and the AD will have this. And then you can see some of the member going to be in compression, for example this one and this one, and some going to be in tension. Okay, and then they ask us to determine the vertical deformation at C, okay, and also the vertical deformation at D. And this is our preliminary elastic curve of the truss, okay. And what we have from the method of virtual work, we're going to talking about the work, okay. And for the real work, is going to come from the real force time the displacement, okay, the displacement. And for this one, we have the real displacement, and then when it's time, the assumed force is going to be the virtual force, virtual work. For the concept of virtual work equation. By the virtual equation, that means we're going to have the virtual force that apply into the structure, and when the virtual force time with the real displacement is going to produce the virtual work. By this concept, let me start by putting this truss, and I'm going to nearly copy the truss there and put it here. What we have now is, by the concept of the virtual work equation, that means we're going to determine the V sub C, okay. This is the C, and it's going to be the vertical displacement, so we're going to put the 1 unit force, okay. This is assumed when this 1 unit time with this displacement, the assumed force or virtual force time the real displacement of the truss as point C in vertical. So this term we call external virtual work, okay. That is going to be external. Because why is external? Because this is the external displacement time the assumed force, so we get external virtual work. This external virtual work must be equal to the internal virtual work. Okay, what is the internal virtual work? This 1.0 or unit force, when it's applied to the truss, is going to produce the force, the member force, that's called N sub CV, okay. When this member force time with the deformation of this truss, okay, we will have equal to, we will have the internal virtual work. So the 1.0 unit force going to produce the internal virtual force in truss member, and this gonna time with the deformation of each member. And if you may recall, if we have the axial force member, and if the force is N, we may have the sigma equal to N divided by A, right? And under this force, this member gonna elongate, and the strain is going to be elongation divided by the length. And then you have the Hooke's law, sigma equal to E strain. This you have it in the mechanics of material. And what we have, you are going to have N equal to A. This is stress. That is going to be E, and time strain, that is elongation divided by L. And finally, you arrive at the equation of delta. That is going to be the the shortening or elongation of each member is going to be what? N times L over AE. Okay, this is the real deformation of the truss. When it's timed with the virtual internal for member force, is going to produce internal virtual work. So usually we have many elements. So we got to put this is I from 1 equal to, let's say, x. And this equation can expand to be what? To be the N, the internal member force due to the force at C in the vertical direction. And it's going to time N, this is I, N sub I, L sub I, divided by A sub I and E sub I if it's used the different element, different types of material. And then the summation could be from I to the total number of elements. This is equation that's going to determine the displacement, vertical displacement at C. How about the equation for the displacement at D? Okay, at D. It's the same thing. You got to draw another truss. Okay, and your truss going to have the point D here. Okay, point D here, and then you got to what? You got to put the 1.0 force into this point. So we got to put this one, and then again the 1.0 gonna what? Gonna time the real displacement at D in the vertical direction. Again, this is gonna produce the external virtual work, and this external virtual work gonna equal to this time is the summation from I to X of what? Of this force. This force going to be N, okay, the member force at D in the vertical direction. And then we going to produce another condition of the force in the member of the truss due to the assumed 1.0 unit force, but this time it's SD, and now it's going to time N, okay, D phi, and the term here going to be the same because it's due to the actual applied force. So this is going to be N sub I, L sub I divided by A sub I and E sub I. You need to put I here also. This is the concept of the unit load method or method of virtual work. So next, what we should do, if you consider the equation that we just obtained, that means we gonna determine the N, that is the force that's due to the actual or real load. This is must be N sub I, okay, and you also need to determine N sub Ci. That is going to be the force here, and you also need to determine N sub Vi, which is going to be here. So that is the step of calculation. After we determine all the internal forces due to the real applied force, due to the assumed unit force at C in vertical direction to determine this, due to the assumed 1 unit force applied at D to determine this. We can plug all of that into this table, okay, and then we determine this. Okay, because we go further, we also need to determine the AE is a constant. Okay, the AE is a constant. So Don't worry about this. They're giving us the AE. So since the AE is constant, we may neglect it in this calculation, and then we will put AE later, okay, in our calculation. And the L is changed, okay, the L is changed. And if we may start, we may check for the L. They give us the AB. AB is here, 3 meter. AD, okay, this is going to be 3 meter. And this is going to be 2 meter. So this is going to be 3, 2. This is must be square root of 9 t square plus 4 plus 2 square. That is going to be square root 19. So that is the length of AD. And then the BC. What is going to be BC? BC is B is here and C is here. So it's going to be 3.0. How about the BD? BD is here. BD is going to be 2.0. And CD, okay, CD should equal to, because this is 3, this is 2, so it's going to be square root 13. And also the DE is going to be the square root 13 in the unit of meter, okay. And from the table, we can find what? We can find this is the force in the member of the truss due to the applied force. And then we determine this one, okay, which is this one due to this one. And the last one, we're going to be determine this one from this one. Okay, so we have a lot of work to do to determine the internal forces. Let's start by first, and finally we supposed to compute this. The summation here and also here. Okay, let us start by analyzing the task. The first step, we find the member force, okay, which is going to be N sub I due to the applied loading. Okay, that is our first one. And if you like to determine this, what you are going to do, we don't need to determine the reaction, because we can cut this to determine the force in these two members. And luckily, they also give us some information of the force in member AD. Okay, if they give us in the member AD, this is the member AD. Okay, and this is going to be plus 18.03. And also DE is here. Okay, DE. So we're going to have 4 more members left to determine the applied force. Okay, let me first by using method of choice to cut this. Okay, let me cut point C. That is going to be C. Let's put the C here. And this is going to be the x-axis. This is going to be the y-axis. This is going to be C. The C is subjected to what? 30 kilonewton. So this is going to be the force of 30 kilonewton applied here. And what we have, when the 30 kilonewton apply here, this one supposed to act upward to try to push it up, right? So I think the force here must be in this direction. And this one what? This one is CD. So it must be, let's call it F sub CD. Okay, and the ratio here is 3:2. So it's 3:2. And this 3:2, this is going to be square root of t square plus 2 square root 13 as we mentioned a little bit before. So this is sorry, this is not that. It's going to be sorry, 3 going to be here. It's 3. This is 2. It's going to be 3 2 square root 13. And also, if this one push up, it's going to balance this one, right? And it's going to be f sub cd. This is going to be 2. This is going to be 3. And it's going to time 2 over square root 13. And this is going to be this force also. Anyway, the force that's going to balance this is going to be in the opposite direction. Okay, and this one is along the CB. So this is F sub BC. Okay, for to balance this. Okay, we have the free body diagram of joist C. From this free body diagram, which equation of equilibrium you are going to use first? The summation of f sub x equal to 0. If you use this force will project this one, and then you're going to have two unknown and you cannot solve it. So the better way is you should use summation of f sub y equal to 0. And now you project this one. Okay, it's going to be upward. So upward is positive. And then you have f sub cd, f sub cd, and it's gonna time 2 divided by square root 13. This is upward. And then the 30 is downward. So it's just equal to 30. And now you will have what? You will have f sub cd equal to, this one is 30. And it's gonna time this one square root 13 divided by 2. So this is going to be 15 square root 13. And you will get this one for 54.08. You get 54.08 kilonewton. Push it into your calculator, pause the video. And what did you get? 15 times square root 13. And later you may use the summation of f sub x equal to 0. This time you're going to find f sub bc. So this is positive. Your f sub bc is going to be on the left. So f sub bc is going to take left. But this guy, when you take it, going to be in this direction. So it's going to be equal to 54.08. 54.08. And then it's project into the horizontal. So time 3 divided by square root 13 time 3 divided by square root 13. Okay, and then what you get is, just stop the video and push it into your calculator. You will get this for 45 kilonewton. And what the 45 is going to be, BC is going to be in tension, so it's in tension. And CD is going to be in compression, so in compression. And then you may push it into this one. The CD is here. CD is compression minus 54.08. And this one, 45 for the BC. This one gonna be plus tension, 45.0. Okay, now we have these two already. And then we have another point to consider is joist B. Okay, so consider the joist B. If we consider the joist B is here, so this is gonna be the joist B. The joist B is gonna subject that to 20 kilonewton force. Just put this one into this joist B, 20 kilonewton. And then it's going to have the member BD. Member BD gonna resist this. Okay, I think the member BD is supposed to push up. Okay, and it's going to produce the force of F sub BD. Okay, and you can see the BC. The BC also has this one, so the BC is in tension. If you put BC in tension, and then you will get the AB also in tension. As I mentioned before, from this elastic curve, these two going to be in tension. Okay, it's going to bend something like this, The top going to be in tension, the bottom going to be in compression. So, by the way, let me move a little bit, and then we have F sub BC in tension. This is going to be F sub BC, that is 45 kilonewton. And then we have F sub AB to balance it. And you may see this time F sub AB. This time the free body diagram have the force in the x direction alone and in the y direction alone. So it's going to be very easy to determine the force here. Okay, you got to have summation of x sub x equal to 0. So if you put this one is positive, F sub AB is going to be 45. It's going to be 45 kilonewton, and it is in tension. So AB is going to be over here plus 45 part O, and the other F sub BD is going to be very easy also. Summation of F sub Y equal to 0, and F sub EB is upward, is positive. And then we have F sub BD. F sub BD gonna be equal to 20 kilonewton and 20 kilonewton, and is what is in compression. So this is minus 20.0. That is what we have to determine the N sub I. Okay, this is going to be N sub I. And next step, later we move a little bit further to here, and for this one, yeah, this is going to be A, B, C, and D, and E. Okay, and now the next, let's us determine. We're going to find the member force. This time is going to be N at the C in vertical direction plus I. This is due to 1 unit load applied at C in vertical direction. That's used to determine this one. So we put this. And what we have, we need to consider this truss, and we can use the concept of zero force member. You can see some of the member have zero force. Which one? We have the joists connected by 3 members, and 2 of them are in parallel. No applied force here, right? So the force here gonna be 0. And then again, since this one is 0, we have 3 members connected at the joint D, and 2 of them in parallel, no applied force. So this is gonna be 0 force. Okay, if you understand that, we're going to consider it easily. We start by considering the point C. Point C is here. Considering point C. By considering the point C, you may have this one. Or you may zoom it a little bit if you like. Okay, and then you have the applied force of 1.0 unit. Okay, 1.0 unit. And then you cut this, and this is going to be very similar to this, see? But this one is 1 unit, this one is 30 unit. Okay, if you notice this, you may find that the free body diagram of this one, this is going to be N sub BC, and this one going to be N sub CD. Okay, and this is going to be 2. Okay, this is going to be 3 square root 13. And if you compare this one with the free body diagram here, you may find some relationship in which the applied force here is 30 is 1. So by doing this, you can say that the n here can be compute from the result that you obtain here. Okay, this is going to be BC going to be BC is 45, so this one must be 45, and then divided by the force are 30 times different, so this is going to be divided by 30. And this one CD is 54.08, so this one going to be 54.08, and then divided by 30. Okay, by doing this, you may get the result of N sub CD, and this is going to be equal to 1.803, and this one going to be 1.5, and this is intention, the 1.5 intention. So N sub BC, and if you do a little bit this, okay, you may put this into your table, N sub BC. The BC is going to be 1.5. So what is BC? BC is here. Okay, this is going to put plus 1.5, and this is going to be CD going to be here, and it's in compression minus 1.803, and you have BD is 0, and AD also 0. Just put it into 0. So we have 2 elements to determine what the AB and the DE. Okay, say if you push the point D, and then you try to again move and try to consider the point D, and the point D is here, and point D is subjected to this force of CB, so this is going to be 1.5 of what? This is intention put out. This is intention. So this is point B. That is subjected to 1.5. Force here 1.5. And then you have the AB. This one, okay, is supposed to N sub AB. And you have no vertical force. This is Y. And you can pass this for summation of x sub x equal to 0. So if you put this is a pass, so N sub AB, N sub AB is going to be 1.5 and in tension as this one. Two of them are in tension. So now the AB is going to be plus 1.5. And the last one you have is the DE. And if you prefer to do so, you may have this one for point D. And this is going to be the X. This is going to be the Y. And your element going to be in this direction. And this one is in compression. So 1.803 is here. This is going to be 1.803. And you know this one going to be 2, 3, and square root 13. And also you may have this one to be in balance. It's going to be in the same direction. And the best way to do this is going to be the N sub DE. You're going to push this one at the X palm. And then you put this one as the Y palm. Okay, and then for me, summation of X sub X palm equal to 0. Just put this one up. So you may get N sub DE equal to this one equal to 1.303, and it's going to be in compression. That means you're going to push this one up. It's going to be minus 1.803. Okay, now you are finished determining the N sub CV for this. And let us go further to determine the N sub dV. Okay, here, the third that we finish is okay, the third phi. This one phi. We find the what? We find the member force. Phi the member force. Member force. This one is going to be N at D in vertical direction, and which the member I. Okay, this one is due to okay 1 unit load. Okay, applied at D in the vertical direction. Okay, this is very clear to make it to be N sub dV, and then you may put this one, okay, to guide you to determine it. What we have is the same by the concept of zero force member. Sum of the force in the Truss gonna be 0, and we have this one A, B, C, D, and E, and these joints have no force, so this is 0, this is 0, so the dB is 0. So this was who is 0, then this one gonna be 0 and 0. So what we have is going to be AB is 0, AB is 0, okay, and then BC is 0, BC is 0, and CD is 0, CD is 0, and what we have, BD is 0. So only two left to determine this. So for this one and this one, if that's the case, it's going to be very easy. Just take the joint D here. This joint D here is going to be the x-axis, is going to be the y-axis, and 1.0 is here. And since this is 1.0 is here, downward, the force here gonna resist up, right? So I believe the the force here must be up, okay, to balance the 1.0. This is going to be N sub DE. And again, N sub DE going to have the angle of what? Of 2, 3, and then square root 13. And you also have this one. Since this one is up, okay, and then if it push in the horizontal direction, it's going to be in this direction. And there is no force to balance it. So I believe the N sub AD going to be in this direction. So this is N sub AD. And again, this is going to be 2, 3 square root 13. Okay, that is going to be the complete free body diagram of Joyce D. Which equation you going to use first? This one, you push it, it's going to be in two directions. So no matter it is, but it's better to use the summation of x sub x equal to 0. And then you may say, okay, upward is positive. So if this one is project, it's going to be upward, right? This one going to be upward. This one going to be to the left. Sorry, this one going to the left, to the right. To the right is positive. So this one is going to be to the right. So we have N sub DE, and if we project it horizontally, it's going to be times 3 divided by square root 13. This one, when it's project, it's going to be in the opposite direction. So equal to N sub AD, N sub AD. And then it's going to be 3 times 3 divided by square root 13. And you may see this one cut. So N sub DE is equal to N sub AD. We have N sub DE equal to N sub AD. And then next we are going to use another one, the summation of f sub y equal to 0. This time upward is positive. So you have N sub DE. If you push upward, N sub DE push upward, you need to project it by 2 divided by square root 13. It's going to upward. Okay, and this guy also, if you project it, it's going to be go upward. So you plus, okay, this one N sub AD, N sub AD. The same thing, you project upward times 2 square root 13. And then it's going to be what? It's going to be equal to 1. Okay. Since these two are equal, so it's up to you which one you are going to use. Okay, let's see. If you use this one, it's going to be N sub DE. And so equal to is going to be 4 divided by square root 13. And it's equal to 1. And then you may have, okay, N sub DE, and that's equal to, this is going to be 1 times square root 13 and divided by 4. Okay, and you may have it for 0.9014, and you may have it for equal to 0.9014. That is N sub DE. And then N sub AD, by doing this, N sub AD is going to be equal. So both of them going to have 0.9014, but the AD is in tension, so this is going to be plus 0.9014, and this one going to be in compression minus 0.9014. Okay, that's we finish our calculation for the normal force from 3 cases, and now we may use the information that we have to compute for the deflection. Okay, and then the next step, let's see, is going to be step number 4. We determine the V sub C vertical and V sub D vertical. Now, if you consider this, that means we got to sum up what? Sum up the normal force time the capital N time L. Okay, and then we divide it by AE. By doing this, we may have this one is going to be the plus this one, and this one is 0. This one and this one is plus. This one and this one is 0. Minus is a plus. Minus is a plus. Okay, and if you do that, you're going to get this one for 202.5. This, and this one gonna be okay, the same. It's really similar. 202.5. This one is 351.54, and another one is 468.72. Okay, and then after do the summation, you will get this to 1,225.26. Okay, and again, you also can do for this. You can do for this for if it's 0, just 0, because every time 0 is 0. This time this plus is a plus. Okay, this one, and this one, you're gonna get it for 58.59, and this one time this one minus is going to be plus, and times square root 13, that is 234.36. Again, if you do the summation, you may get it for 292.95. Okay, and now you are ready. You've got the number of this one. Okay, just divided by AE. You may have the deflection CV equal to 1,225.26. Okay, and divided by AE. Another one, you have V sub dV. That is going to be equal to this time 292.25, 292.95, and then divided by AE. And what we have is just put everything together. This one is going to be 1,225.26, and the E is going to be 200 gigapascal. So it's going to be 200 10 power 9 change to 10 power 6 kilonewton per square meter, and A is 300 square millimeter. So time 300 square millimeter change to square meter. Okay, and then if you push everything, this cut, this is cut, you may get this for 0.0204 and meter, or it's going to be 20.4 millimeter, and this move downward. Okay, and this one also you may get it easily. Just put to 92.95 and then divide it by this time is easy, 200, and this is going to be 300. Okay, cut. Then you get this for what? 4.88 and 10 minus 3 meter, or you get it for only 4.88 millimeter. That is smaller than 20.4, about 5 times. Okay, and that is what we can do to compute the deflection of the truss. Okay, and if the 20.4 millimeter is kind of large deformation, you like to reduce it by a half. Okay, let the try to do this. If you try to reduce the deflection, that means the member gonna get larger. Okay, to make it stronger, stiffer. Let the allowable vertical displacement at C. C is going to have the largest vertical displacement due to this kind of elastic curve. Okay, this one going to get the largest one. That's the reliable vertical displacement is C is equal to 0.010 meter or equal to 10 millimeter. Just put it like this, and we're going to redesign. We're going to redesign the truss. Okay, the truss into this truss. And if we redesign the truss, what we have is the we allow is going to be this one, 1225.26 divided by AE. Okay, and then what we have, we're going to find what we're going to A, that's we require, and where is required is going to be just 1225.26, and then divided by this is E, and then we allow. And again, we need to be very careful with the unit we are going to use. So just put it. This one is 1225.26, and the E is going to be in kilonewton. So 210 power 6 kilonewton per square meter, and we allow going to be in meter. So just put this one 0.01 meter, and if you push it in millimeter, after you do the calculation, you may get this for 613 square millimeter, which is going to be larger than what used here of 300 square millimeter by larger than 2 times. Okay, and if you like to use the hollow section like this, and your hollow section gonna have the external diameter of, let's say, 50 millimeter, and you going to determine the thickness. Okay, if you like to see the thickness, that means you're going to determine d sub I, and then the thickness can determine from from 2t equal to 50 minus d sub I. So the thickness is going to be 50 minus d sub I divided by 2. So you got to determine the d sub I. If that's the case, you're going to have pi over 4, right? And then this 50 square, and then minus d sub I square is going to equal to 613. 613. And what we have is what? You got to have it for 50 square minus d sub I square. This is 2500. Okay, and it's going to equal to 613. And you rearrange this. This is going to be d sub I equal to 2500 minus 613, and then it have the square root here. You push it into your calculator. This is going to be 41.46 millimeter. That is going to be the internal diameter, and then the T is going to be 50 minus 41.46 divided by 2. So you're gonna have this for 3.54 millimeter. Just check it out. What section manufacturers by steel company, and you select the bigger one that's bigger than this. Okay, that is the end of this example. The unit load method is very versatile. It can be used to determine the deflection of the truss, of the beam, of the frame, but only on some specific point. So you need to use any adjustment to decide which point going to have the largest deformation. Okay, and sometimes it's not easy to make the assumption of the maximum deflection, and then you need to compute many times to get the appropriate result. Anyway, it's better than like the conjugate beam, because the conjugate beam only used to analyze for the deflection or the slope of the beam only. Okay, let you guys work on your homework and try to build your own skill for solving this kind of problem, and for sure you're going to have examination on this. Okay, bye bye. This is a clip that's going to demonstrate you how to solve for the loop truss, and we are going to determine the vertical and horizontal displacement at a point on the truss. But this one, they asked us to determine at point P. The loop truss have the top chord and bottom chord. What is the bottom chord? Bottom chord is here. Okay, and the top chord is here with the area of A. Okay, A is equal to 90 10 minus 6 meters square, and the other section they can have the area of 0.5A. So this member is 0.5A, and the yellow have the cross section of A, and it's made by the steel, so they give us the E equal to 200 gigapascal. As we know, they ask us to determine the deflection at B. Okay, what happened is, before we going to do further, let's us try to understand what happened. Okay, when this one push here, okay, our beam gonna have what? Gonna deflect like downward, right? And since this one cannot move horizontally and vertically, only this one can move. Okay, and if this one move like this and this one going move is supposed to move, maybe downward here. So what I expect, this beam gonna have this kind of deformation, and we can expect the elastic curve. Since this one is downward, this one also downward on the right, and then this one should move here, and this one may move somewhere here. And then if you connect the member of the truss, you may get the preliminary elastic curve of the truss in the form like I'm drawing here. Okay, and what they asked us, they said under the force we're going to determine the vertical. So this is going to be the vertical. Okay, this is going to be V sub B, vertical. And it also asks us to determine V sub B horizontal. Okay, and that is going to be our elastic curve, but it didn't draw it properly yet until we get the value of the deflection. But just the expectation by using your engineering sense and engineering judgment. This task subjected to 3 forces. Okay, the 3 forces. This one, this one, this one. The forces are symmetry. Okay, and then we're going to use the method of virtual work or the unit load method to solve it. What is the basis of this? The basis of this is for the method of virtual work. We have what so-called the virtual displacement equation. Virtual work equation. For the virtual equation, what we have is we're going to put what is the virtual, is put the virtual force into this task. Okay, and that means what, to using this method, you're gonna put the virtual force. The virtual force is going to be the 1 unit force, since it's going to have also the name of unit load as we have in the PowerPoint. And we are going to determine what? We are going to determine the vertical deflection at point B first. So this one is the pin, this one is the roller. So we got to put 1 unit force at the B in the direction given here. So the first one, if we like to determine the vertical displacement, we put 1.0 unit at what? At B to find vertical. And I surely assume it's going to be the downward as I do the elastic curve. And what happened is we're going to have this 1 unit. If you multiply this 1 unit by this vertical displacement, let's say multiply 1 by phi sub b of phi. And if the force times the displacement, what we have is going to be what's so-called the external virtual work. The work is the force times displacement, and since the one is assumed, so it's the virtual, and it's external because it's occur on external of the truss, not inside the member of the truss. And this one going to be equal to the internal virtual work. Okay, and internal virtual work are derived previously, and we know that this is going to be summation of the force due to the applied load here. So this is going to, for what? This is going to use to determine the internal force due to the applied loads. And then under the unit load, okay, you will get what's so called the N, the normal force in the member subjected to the force at B in the vertical direction. So this one will provide with the normal force. So the internal virtual work gonna be the real force, okay, time the elongation or contraction of the member. And if you recall, if you have the member like this, and then you have the force N here with small force N here, you have the stress equal to epsilon times 10. So you have the normal force divided by A, and it's equal to E. And this is going to be the deformation divided by L. Okay, if you put this, you're going to get the deformation going to be equal to the force N times L over AE. Okay, so this term is going to be the virtual displacement. This is going to be the virtual displacement or elongation or contraction of the member, and then if it's times by the real force, so it's going to be the internal virtual work. So this is going to be N at B vertical, and you're supposed to put I because there is various member here. And then it's going to time what? It's going to time L sub I over A sub I and E sub I. So virtual force times the real displacement is external virtual work, and then equal to internal virtual work, which is the real internal force times the virtual deformation of the member. Okay, and also if you like to determine the horizontal displacement, you also need to do the same thing, but this time you got to put the force in the different way. Previously we put the force at point B in the vertical direction to determine the vertical displacement, and this time you're going to find the horizontal displacement. So comparatively, you can put the one unit force at what SB, but this time it's going to be in the horizontal direction like this. And you may have this one for 1.0 this time, and it's going to time the displacement at B in the horizontal direction, V sub B horizontal direction, and then it's going to be equal to summation of N sub I, still be the same N. Okay, N is the fact, it's always the facts, it won't change because it's the internal force due to the real applied force. And this one gonna change to what? This is N sub B, but this force horizontal. So you time is N sub B horizontal, and then I. And the last one, L sub I divided by A sub I, E sub I. That is the property of the section. Okay, it's going to be the same no matter the applied force R. Okay, then from this equation, we will start by determining the N. Okay, to determine the N due to the symmetry of the applied load. Okay, and we have what? We have A sub Y equal to this one is C sub Y equal to 30 divided by 2 is going to be 15 kilonewton. So what we have here is going to be the reaction here. Just put this is going to be 15 kilonewton, and this also going to be 15 kilonewton. Okay, and then we are going to start to determine the forces in each member. Okay, however, if you take a look at the table, the problem gives you some of the forces already. For example, it said it had the DE of minus 6.667. So this is minus 6.667 kilonewton already. Okay, and also it had the BE. What is BE? BE is here. BE is minus 5.0. So this is minus 5.0. They give us already. And next is the BD. Is the BD is plus S.333. Okay. Now, what we have is we're going to determine the rest of it. Okay. So by starting the determination of N, can you start with the A? No, A have 1, 2, 3 unknown. And you may start by the F because the F have 2 unknown. Okay. By doing that, just take a look at the method of joint. And this one is going to be the F. Okay. And then we put this in the X direction, and this one in the Y direction. And then it's subject at 10 kilonewton. So the force is here is 10 kilonewton. What we have is the member AF will resist this vertical force. That is going to be F sub AF. Okay, and F sub FE F sub FE is over here, F sub FE. And you can see that if you do the summation of the F sub X equal to 0, what you get is F sub FE is 0. So F sub FE equal to 0 kilonewton. That is the first one we have. And then we put this is positive. And the next one, if you do the summation of F sub Y equal to 0, this time you put this one up is positive. So F sub AF is going to be what? Is going to be 15 this time. And then, no, sorry, it's going to 10 kilonewton. And then we have this. Okay, so next we have this for 0 kilonewton. And AF is like this. So this one is going to be in compression. So this one going to be minus 10. Now, when we know this minus 10, we start to consider this point of point A. And point A gonna subject that to F sub AF. Yes, it's going to be 10 kilonewton. And it's also have 15 kilonewton here. So put the 15 kilonewton here. And you have this one for the X direction and this one for the Y direction. And you have the member AB, right? So you put the AB in what? When you have the member subjected to the force like this, it's going to bend like this. When it's bent like this, the bottom going to be in tension, the top going to be in compression. So this one in compression. So I believe this one going to be in tension. And that we set that one up as this one. And it's going to be F sub AB. This is going to be F sub AB. And then you can see the 15 kilonewton is up, is larger than the 10 kilonewton. So the force here, which is going to be F sub AE. F sub AE. F sub AE have the ratio of what? 2.4 and 1.8. And if you divide it by 0.6, this is going to be 3, this is going to be 4. Okay, so you have the ratio of 3, 4, and 5. So which equation is going to be the first one you're going to use? Summation of f sub y or summation of f sub x? If you put the summation of f sub x, you're going to get two unknowns and you cannot solve it. Okay, so we start by the summation of f sub y equal to 0 to take this one, okay, to be the unknown. So the downward is positive. So you have f sub ae, f sub ae in the vertical direction is gonna time 3 divided by 5. So time 3 divided by 5. And then in this direction, downward is positive. So it's going to be plus 10. And what? The 15 is up. So it's going to be 15. Now, the f sub ae, okay, gonna be equal to, so you move here, that's going to be 10, 15 minus 10. So it's going to be 5. And then you move 5 times, this one is going to be 5 over 3. So you get is for 25 divided by 3. That is going to be equal to 8.333 kilonewton. And this one is going to be in compression. So it's in compression. Let's put the AF also in compression. Okay. And the last one, we have this force, and we do what is the summation of x sub x equal to 0, right? And put this one as the positive. So we have f sub ab here. So f sub ab, and then you project this one horizontally. This f sub ae must times 4 over 5, and it's in the opposite direction. So it's minus 4 over 5, and itself is 8.333. Okay, so it's equal to 0. And then when you push it into the calculator, you will get f sub ab equal to 6.667. This is 6.667 kilonewton, and it's going to be in tension. Okay, we are like this for 6.667. So this one is plus 6.667, and this one is going to be minus 8.333. Okay, now we going to have two more left over here. Okay, and it's going to be better just to using the method of joint to cut it at the C. And then we have this point, okay, at the C here. This is going to be the X, this is going to be the Y, and we have this member BC. So this is going to be the member F sub BC, and this one have 15 kilonewton acting here. That is the reaction C sub Y. That is 15 kilonewton. What we have is we have the CD. So the CD for sure is going to be in compression. This is going to be F sub CD. And now you can determine the force easily, right? Okay, if you do this, you may use the summation of F sub x equal to 0. And then what you get is F sub BC. This is plus F sub BC equal to 0 because there is no horizontal force. And then if you use F sub y equal to 0, this time downward is positive. So you got F sub CD downward. This is upward equal to 15 kilonewton. And then the force here is going to be what in compression. This is going to be minus 15. This minus 15, and this is going to be 0. So that is what we determine the normal force N in the member. Okay, you may call it member force in the truss due to the applied force. Now we're going to determine N sub BV. Okay, and then you may use the same thing due to the symmetry of the force. So we will have the reaction here of 0.5 and the reaction here of 0.5. And you may use also the concept of zero force member by using the concept of zero force member. Zero force member. What we have is, if we have two elements connected at a joint and there is no applied force, so the force here gonna be 0. Okay, and the same thing, this one and this one pretty close. You can see this is 0, right? So the force here should be 0. And then the force here also, this one is 15, this one is minus 15, so this one gonna be minus 0.5. Okay, that's what we have. And then if you consider the free body diagram here, you may get the point A. Okay, the point A is here is the A, and then it's going to subject it to 0.5 here, and it's have the AB. Okay, and also AE, the same thing at here, AB and AE. So we're going to have the force here is going to be N sub AB. This one N sub AB, and the force here, this is N sub AB is similar to here. Okay, this member, and this one going to be N sub AE, and this one going to be N sub AE. And you also have this one for 3, 4, 5, and if one is Y, this one is X, and you compare this one and this one, you can see something. What you see is, this is 10, this is 15, so the force here gonna reduce to 5. Okay, this is 0.5. So this is 5 kilonewton. Produce F sub AB here, and produce F sub AE here, and produce F sub AB here. So since the force is 10 times less, so you will get the F sub AB here, which is here going to be 10 times less also. So this is going to be plus 0.666 and 7. Okay, without do the calculation. And this one is going to be less for 10 times. It's going to be minus 0.8333. Okay, that is going to be easier to determine it. And later, you may use this portion to determine the force in member this and this member, or you may use this portion, this point, to determine this. Okay, if you use this is going to be the choice D. And if you like, you may draw the free body diagram of joint D here, and you have the compression of 0.5 here. Okay, and then you supposed to have the force about here. Since this is in compression, I believe this one going to be in tension, and this one along this is going to be F sub BD. And you may know that the ratio here gonna be 3, 4, and 5. And since this one is in this direction, so the force here going to be in this direction. This is going to be F sub ED, F sub ED. And then if you set up this one as the X, this one going to be the Y. Which equation you going to use first? Okay. If you consider this in the vertical direction, you may solve this one immediately. If you put it in the X direction, you won't. Okay, so by doing this, just summation of X sub Y equal to 0. This one, when you project, is going to be downward, so set the downward is positive. So you get F sub ED downward times 3 over 5. So F sub ED, that is going to time 3 over 5 times 3 over 5. This is downward, and it's going to equal to 0.5. So it's equal to 0.5. And then you will get F sub ED equal to 0.5, and then it's going to be time what? The 5 going to be up, time 5 over 3. So you got this for 6.667, 6.66. So sorry, 0.6667. Okay, this is going to be this one, ED minus 0.666 and 7. Okay, and since this one is going to be, oh sorry, no, let me time this one. I'm doing it wrong. It's going to be what? 5 times 0.5 divided by 3. That's it's going to be 5 times 0.5 and divided by 3. It's going to be, oh sorry, 0.8333. So this one is going to be okay, 0.8333. This is going to be which member? It's not this one. This is wrong. This one F sub ED, F sub ED times 3 over 5. No, F sub ED times 3 over 5 is downward, equal to 0.5. This is BD, not ED. I'm sorry. So this is BD, F sub BD, F sub BD. Okay, so this one F sub BD, and this one gonna be 0.8333. Okay, this one we have it in tension, so to put this one is plus 0.8333. Okay, and now summation of x sub f equal to 0, x sub x. So you're going to find f sub ed this time, and you have this one is positive, so f sub ed here going to equal to this guy project in the horizontal direction. That is going to be 0.8333. When you project it in horizontal direction, times 4 divided by 5. So times 4 divided by 5. And now you get f sub ed of 0.6667. 0.6667. Okay, this one is sure correct. And it's going to be in compression. This one is minus 0.666 and 7. Okay, now we finish determining the normal force in this truss and the normal force in this truss due to the 1 unit force in at B in the vertical direction. Okay, let's not use this equation now. We have this. So we're going to determine the dimension of the member of the truss. Let's see what we have. What the AB. The length of AB is 2.4. This is going to be 2.4. BC is going to be 2.4. And CD is 1.8. And DE, okay, it's already. And EF is 2.4. And AF is 1.8. And what we have the AE, so AE is equal to BD. BD is 3.0. This is going to be 3.0. And the area, all A are given. Okay, and we got to put the author for 0.5 A. Now we just put this thing. This is going to be 0.5 A, 0.5 A, 0.5 A. A going to be the divider. Okay, this is 0.5 A and 0.5 A. And now what we have is the force N. What we have AB is here plus 6.667. BC is here. BC is 0. And CD is minus 1.5. And this is DE. And this is EF. And this is AF. AF minus 10.0. Don't forget about the sign here, okay? And AE is minus 8.333. Okay? And now we have this already. And the last one is the normal force at B vertical. And what we have is the AB 0.6667. BC CD minus 0.5 and DE, this one, minus 0.667 and EF, this is F 0 and AF is 0 and AE is minus 0.8333 and BE is here. Okay, you can determine BE. Let's say this is going to be 0.5. One more, you just cut any joints and do the calculation. Okay, we got this one for plus 0.5 for this one. And the last one, BD. BD is here, plus 0.8333. Okay, now we put everything into this equation. So big capital N, small n, L divided by A. The E is the same, so we can put E later. Now what we have is we're going to determine this. So it's going to be what? Capital N, small n, times L, okay, divided by A. So the first one you will get is as 10, this one times this one times this one is going to be plus it's going to be plus 10.668 divided by A. And this is 0. Okay, this is 0. And this is 0. Everything time is 0. Minus is going to be plus. Take this one first. Okay, you may forget it later. This one minus is plus. Okay, minus is plus. Minus is minus. Plus is plus. Now, you just put this one into this one. Don't forget to divide it by 0.5a. So this one you will get 27 over a. And this one divided by a. You can get this one for 10.668 divided by a. This one and this one, they are the same, but the size kind of different. And this one gonna have what? 41.664 divided by a. This one minus 9 divided by a. This one also 41.664 divided by a. Now we have the summation, right? So you got to sum them. Summation of everything, and then you may get this for 122.64 divided by a. And then you may put later. Now we come into here. So this is equal to what we have here is 122.64. The A is here, okay, and the E is here. And since we compute this one in kilonewton, so the E is going to be 200 times 10 power 6 kilonewton per square meter, not newton, it's in kilonewton. So this one gonna have 210 power 6 kilonewton per square meter. And the area here is in meter square already, so we can put it easily for what? For 90, and then it's going to be 10. This is 10 minus 6 and meter square. Now 10 minus 6 and 10 power 6 can be cut, and if you put everything in your calculator, you can get this one equal to 6.81 10 minus 3 meter, or you may have 6.81 millimeter, and the value of this is positive. When the value is positive, it's gonna follow this, okay, it's gonna the 1 unit force, so it's down. So that is the first one we have for the deflection of B in vertical direction. And next, we're going to determine the horizontal displacement at joist B. So we put 1 unit force here, okay, and then we have N sub BH. We do N sub BH, we are going to determine it, gonna time with the normal force N in the member, and then you can put into this equation to determine the horizontal displacement over here. Okay, let us consider from the free body here, what you should we have is the, what is force here is going to be C sub y, and it's going to be A sub y, and it's going to be A sub x. And you may have from this one, you may take the moment, summation moment about A equal to 0. So the C sub y gonna be here. Okay, you can see sub y times 2.4, C sub y gonna times 4.8. So you're going to have 4.8 C sub y. The force here is putting here 0 moment, and no else force is going to be 0. So C sub y equal to 0. And then you may have summation of x sub x equal to 0. And then you get the A sub x here is going to be 1.0. So this is going to be the A sub x. And if you do the summation of f sub y equal to 0, A sub y gonna be 0. So this is 0, this is 0. When this is 0, you can apply the concept of zero force member. The same concept of zero force member here. And this is gonna be 0, 0. Okay. And you also, since this one is 0, this is 0, this is 0. And since there is no force here, if you do summation, this is 0, this is 0. Okay. And now, just draw the free body diagram of this joist. Let's see, this is the A. We have this one for the X, this one for the Y. We have A sub X of 1.0 here. And we also have this one for N sub what? N sub AB, N sub AB. And over here is 0. And you may have the force, another force here also. Okay, this one N sub A E, A E. Okay, and the ratio here is going to be the same, 3, 4, and 5. By using this, you may use the summation of f sub y equal to 0. You may have N sub AE times 405, and it is 0. So your N sub AE is going to be 0. And if you have summation of x sub x equal to 0, this time is positive. So your N sub AB gonna be 1. So you get this for 1.2. And it's gonna be in positive. Okay. And you get this one for 0. When you get this one for 0, 0, 0, the force here also be 0. Now, you have only force here. And it's along the AB direction. And then we just come to this table. And this is going to be plus 1.0 and 0, 0, 0, 0, 0, 0, 0, 0 here. Now, if you time this one, all of them are 0 except this one. This one is n times this one times this one, right? It's going to be what? 6.667 times 2.4, 6.667 times 2.4. So you get it for 16. Okay, that is going to be the 16. Just put this for the 16. That is plus 16. Okay. And then if you do the summation, you're going to have this one, just simple summation of all of this. This is going to be divided by A also, because you have the area here. This is going to be 16.0 divided by A. And now you're going back here. So this one going to be equal to 16 divided by 290, and then you will get this for the displacement at B in the horizontal direction. And what should we have? You may put this to 0.89 10 minus 3. That is going to be, this is 0.89 10 minus 3 meter, or is equal to 0.89 millimeter. The direction of this is going to be positive, right? So it's going to be something like this. Okay, now what we have is, we have this one. We have the deflection here. this one for 6.81, so this one is 6.81 millimeter, is downward. This is to the right of 0.89, so this is going to be equal to 0.89 millimeter. So that is going to be the vertical and horizontal displacement SB when the truss subjected to the load show, and this elastic curve is quite drawn properly. Okay, and then next they ask us to next step. The member DE is longer than usual, so the next question is going to be about the fabrication error. Okay, we have the fabrication error problem. Now we just follow what step we have before. Just take a look at the equation what we have for the fabrication error. Fabrication error at member is set DE, right? DE is longer than it used to be, member DE. Now, the equation that we have for this, the virtual work equation that we have is going to be 1.0. The same thing, 1.0. And 1.0 is for what? For the force that apply to the deflection, to determine the deflection at B in the vertical direction. So it's going to be this picture. And then this one is going to be equal to the summation of n sub I. Due to this is n sub I, n sub B VI. And then it's going to times the delta L I. By using this, it's going to be what? The delta L as the member DE. So it's going to times N as the member DE. So what we have is the member DE. So member DE is this. Member DE is this. It has the end of N sub BV of this. Okay, and if the case we have this one as N sub DE, and this one going to be 5 millimeter. This one going to be 5 millimeter. So if you time it, it's going to be equal to minus 0.6667. That is with N. And time what we have is longer 5 millimeter. Just time this. Okay, and then if you put everything in your calculator, this is going to be equal to minus 3.33 millimeter. Okay, that means what? That means it's going to be 3.33 millimeter. In the negative, that means it's going to be upward. So the deformation due to this is going to be upward. And then it asks us again horizontal displacement. So again we put the 1.0 here. 1. Let me put this one 1.0. Okay, time what? V sub B in the horizontal direction. So this is going to be summation of N sub I BV, and this time delta L sub I. Okay, and this time we have what? The force here is going to be this one, maybe this one, and what is going to be the force in DE to be here? It's going to be is 0. So this is going to be equal to n sub d e, okay, when the force, due to b h, this is bh, okay, time delta L d e, and it's going to be equal to 0 time plus 5 millimeter, and the answer is going to be equal to 0 millimeter. There is no displacement here, okay. And if you like, you may draw this picture. What you have is the elastic curve of this. This is going to be pin, this is going to be roller. Actually, you can put about here, but it's okay. It's not that good. So this time is up, for 3.33 millimeter. So that means there is no movement in the horizontal, only this just up, okay. When this one up, this one also up, and then I believe this one going to be something like this. This one may move a little bit here because it's up, okay, and it's going to be the shape of this last line, and this one maybe this one this way. We don't know the author yet, but for sure just at what we do the calculation, and what we have is this is going to be the elastic curve of the fabrication error, okay. It's going to be up like that. And the last one they ask us for the temperature change. They says member DE has the temperature change of plus 30 degrees Celsius, okay. By now just a little bit, just zoom to have some area that I can show you. Okay, next one is about the temperature change. It's about the temperature change. Temperature change at DE, at member DE, okay. And now what equation do we have? It's going to be the same thing. It's going to use the virtual work equation, but this time you're going to put 1.0 in which direction? In direction of deflection, okay, at point B in the vertical direction. So this is going to be the external virtual work 1, okay, times the deflection in the vertical, and then this is due to only the temperature, okay. That means what we have is going to be equal to the summation, this one, n sub bv, n sub I bv, and then it's going to time what? The deformation due to the temperature change, and you know that this is going to be alpha L delta T I, okay. That's we studied is due to the temperature, in which the alpha is the coefficient of thermal expansion, and you know that alpha is going to be 12 times minus 6 per degree Celsius. And since you are interested at the n sub bv, and since this one occur only at the DE, so this equation can reduce to a more simple one. That is going to be equal to n sub dE and time alpha, okay, and then delta T and L of the dE, okay. And then if you put further into this equation, the n sub dE is the same in the vertical direction. It's going to be minus 0.6667, and then the alpha is going to be 12, 10, minus 6 per degree Celsius. And then the delta T, the problem says delta T is going to be 30 degree Celsius. And the length of this member is 2.4. So that is going to be 2,400 millimeter. Now, you will get the vertical displacement at B due to the temperature change of minus 0.88 millimeter. It's going to be 0.88 millimeter is minus. This is downward. It's going to be upward. Okay. This is going to have very similar to this. This is going to be okay 3.33, but this one is only 0.88. Now, for another one, the vertical, already the horizontal, the displacement at point B in horizontal direction is going to be the summation of n sub I B, and now this one gonna be H, not B, H, and then the other is alpha L delta T I, and it's occur only at the DE. So N, okay, DE, but this time is here, B horizontal. Before that is B vertical. This is going to be 0, okay, and it's going to be alpha delta TL of the DE. And since this one is n sub DE is 0, so it's going to be 0 time alpha L delta T of the member DE, and it's going to produce 0 millimeter. There is no horizontal displacement due to the temperature change. Okay, and if you draw the elastic curve, you're going to get the same thing, but the scale gonna reduce from 3.3 to only 0.08. Okay, if for example, if the beam, if the truss is subjected to the load plus the fabrication error plus temperature change, okay, the V sub B vertical gonna be what? Gonna be the first one is here downward 6.81, and you have this is upward minus 3.33, okay, and this one also minus 0.88. So the total of this is gonna be reduced to 2.6 millimeter and downward. That means temperature change on the roof of the truss will help to reduce the diffraction. Okay, to help to reduce the diffraction of of the truss. That is very nice. That help, okay, to reduce the deflection. Okay, this is all we have. Actually, we can go a little bit further to design our problem. Let's see if we consider 6 points. 8.1 is too much for the deflection of the beam. We can redesign the beam by the truss by using what we have now. And under the force, we have V sub B in vertical direction of, let's say, 6.81 millimeter. And then if we limit V sub BV to 3.0 millimeter, okay, what is going to be the A? What is going to be A? And then for doing this, that means this is too much, okay, we're going to redesign it. We're going to get a bigger section. By doing that, we may say this is 310 minus 3 meter is going to equal to this one, equal to 122.64 divided by A, and E is going to be 210 minus 6 kilonewton per square meter. You got to be per square meter because the E modulus of elasticity of the material. And if you do this calculation, you may determine the A, right? So the A, just put the A up here and do the calculation. The A can be 204.4 and 10 minus 6 meter square. This is meter square. And then also you know that 1 million square millimeter is equal to 1 square meter. So this one going to be 204.4 millimeter square. Okay. And per se, if you going to have the hollow section to use to build this truss, and this hollow section has the external diameter of D sub I, and it has the internal diameter of D sub O, and let D sub I to be like 50 millimeter. So how can you determine this is D sub O, this is D sub I, or determine D sub I, what is going to be D sub I? Now you can have the area of pi over 4, and you have what? D sub O square minus D sub I square, okay, going to be your area of 204.4, and this one going to be 50 square. So you will have your 50 square minus D sub I square equal to 204.4 times 4 over pi. Now you can do it easily, okay? You can determine D sub I, and it's going to be 47.89 millimeter. So just do this calculation. And if they like to find the T, what is going to be the T? How much is the T? And you know that this is going to be the T and the T. Okay, you may see this 2T equal to D sub O minus D sub I. Okay, so your T is going to be D sub O is 50 and your d sub I is minus 47.89. Okay, and then you may have what is divided by 2, so it's going to be 1.06 millimeter. And now you can buy the steel hollow section with the diameter, external diameter of outer diameter of 50 millimeter, inner diameter of about 47. Okay, and then you may get 47.89. You may get the thickness of this, and you may not have this section exactly. You got to buy the bigger, buy buy the bigger hollow section. Okay, you got to use the one that has the bigger section. So that is the end of this example that include the deformation of the truss under the loads here and under the fabrication error and over the temperature change. This is one of a good example of the truss that involve many things, also including the difference in the area of the truss. Okay, that is the end of the clips. I think you guys will study it and try to do it by yourself to produce your skill. Okay, that's it.